If you've ever watched a car race or those street drag racing videos, you must be very familiar with this scene. At the starting line, the driver will desperately floor the gas pedal, revving the engine all the way to the red line, accompanied by a deafening exhaust roar, and then launch out the instant the green light goes on. In the world of traditional ICE vehicles, madly revving up the RPM is almost equivalent to squeezing out maximum power. But when we turn our attention to the incredibly fast electric vehicles of today, like the Tesla Model S Plaid or the Porsche Taycan, when they do a 0 to 100 kilometers per hour acceleration test, ready to leave their opponents far behind, what does the driver need to do? They don't need to do anything. No need to rev the engine. No need to slip the clutch. Just stomp the accelerator pedal to the floor, and the car will shoot out like a railgun, launching instantly in dead silence. Why do ICE vehicles have to rev so loud? Well, EVs can quietly and violently end the game in one move. Many people attribute this difference to the lack of a gearbox in EVs. Even many veteran drivers who have driven ICE cars for decades, facing EV range anxiety, will raise us a question that sounds perfectly in line with physical intuition. Since EVs are so afraid of running out of power, if when cruising on the highway, we gave it a 6-speed gearbox to lower the motor's RPM, wouldn't lowering the RPM save more power? This statement sounds flawless because our centuries of driving experience has always told us so. But in the real world of electrical engineering and physics, this is a fatal illusion enough to completely burn out the motor. To bust this myth, we won't talk in the abstract. Let's bring the most hardcore truth and data right up front and calculate it for you. Let's do the math on the physics. Do you know that when you are on the highway, driving a Tesla cruising at 120 kilometers per hour, how fast the drive motor under your seat is actually spinning? Many people think that when the wheel turns 1 revolution, the motor turns 1 revolution. This is a huge misunderstanding. Commercially available EVs, except for a very few special vehicles that use in-wheel motors, almost all models are equipped with a set of fixed-ratio, single-speed reduction gears. This reduction ratio usually falls between 9 to 1 and 10 to 1. Let's calculate using common 20-inch SUV tires, plus the sidewall thickness. The overall outer diameter of the tire is about 71 centimeters. Through pi calculations, the tire travels about 2.23 meters per revolution when your speed is up to 120 kilometers per hour. Converted, the wheel turns about 900 revolutions per minute. Okay, now we take these 900 revolutions and multiplied by Tesla's reduction gear ratio of about 9 to 1. What does this mean? It means that while you are leisurely listening to music on the highway, driving on autopilot, your electric motor is now racing at an ultra-high speed of 8,000 RPM. Moreover, like top-tier motors with carbon fiber-wrapped rotors used in Teslas, the maximum RPM can even exceed 18,000 to 20,000 RPM. For it, 8,000 RPM is basically just finishing a warm-up. But in the mind of a veteran ICE driver, as soon as they hear the term 8,000 RPM, the alarm bells went off. In the world of ICE cars, 8,000 RPM is called the red line. The engine is about to fall apart, and the fuel consumption is dreadful. This is why a veteran driver's instinctive reaction is always quickly shift to the highest gear for me. Add a gearbox to push the RPM back to the 2,000 RPM comfort zone. Okay, now let's follow the veteran driver's logic. Assuming we really spared no expense and equipped this Tesla with a perfect 6-speed gearbox at a speed of 120 kilometers per hour, we force an intervention, taking the motor RPM from 8,000 and bluntly suppressing it down to 2,000 RPM. That is, the RPM is directly reduced to 1/4. Will a miracle happen? Will power be saved? The answer is absolutely not. Furthermore, your motor will turn into an extremely power-hungry, gigantic electric water heater. Why does this happen? Because there is an unbreakable iron law in physics here. To maintain the vehicle cruising at a constant speed of 120 kilometers per hour, the total power required to counteract air resistance and tire rolling resistance is physically locked. Whether it's an ICE car or an EV, the resistance you need to overcome is just that big, and the required power is fixed. Let's recall the power formula we learned in middle school. Power equals torque multiplied by RPM. When the total power remains unchanged, and you forcibly lower the RPM by 4 times to maintain the balance of the equation, what happens to the motor's actual output torque? It must be forced to quadruple. In other words, the motor must, at a low RPM of 2000, carrying 4 times its original heavy load. In the world of EVs, torque doesn't just fall from the sky. Torque is directly linked to current. To squeeze out this quadruple torque, the inverter has no other choice but to take an extremely massive current and crazily pump it into the motor's copper coils. At this moment, the most ruthless and cruel Joule's law in electrical engineering strikes. The heating power of a conductor equals the square of the current multiplied by the resistance. In professional terminology, we call this copper loss. Please note, it's the square. When your current quadruples due to torque demands, according to the square law, the coil's heat generation will directly skyrocket by 16 times. This is the most shocking truth in this dimensional downgrade strike. High RPM, low torque to an electric motor means the system is in a high voltage, low current state. Low current means low heat generation. This is an extremely cool and power-saving state. On the contrary, if you forcibly add a gearbox, forcing the motor to carry high torque at low RPM, this is basically crazily boiling water. You think the gearbox helped you lower the RPM and brought back the feeling of saving power. In reality, you just turned precious power that could have been used to drive the wheels entirely into useless waste heat. This is also why EVs, when cruising at high speeds, must absolutely not lower their RPM. If you have a deeper understanding of electrical engineering, you will find that whether it's an induction motor or a permanent magnet synchronous motor, neither can escape this physical law. Take the induction motor as an example. Its stator is permanently fixed, relying on the slip ratio between the rotating magnetic field and the rotor to induce current and generate torque. If you force it to output large torque at low RPM, the slip ratio will be forcibly raised. This not only causes massive copper losses in the stator, but even the inside of the rotor will generate tremendous heat. This is an absolute disaster for efficiency. Hearing this, you might have a huge doubt. Since lowering the RPM consumes power and generates heat, then why does lowering the RPM in ICE cars save fuel? Do the laws of physics not apply to ICE vehicles? This requires us to thoroughly rip open and examine the innate disabilities of the internal combustion engine. The natures of fuel engines and electric motors are completely different. The engine must rely on the piston moving down to intake air, moving up to compress, ignite, and explode, and finally exhausted. These 4 steps must cycle continuously to generate power. It has a very fatal weakness. The RPM must absolutely never be 0. If the RPM is too low, the engine lacks the ability to even overcome its internal mechanical resistance. To maintain continuous combustion, it will directly shudder, stall, and die. So the engine always needs an idle speed to maintain vital signs. Moreover, if you've seen an engine's torque curve graph, you will find it looks like a mountain. At the starting 1000 RPM, the engine cannot suck in enough air. Combustion is weak, and torque is pitiful. You must rev the RPM up to about 2000 to 4,000 RPM, which is the peak of this mountain, for the engine to unleash its maximum power. This is the so-called sweet spot. However, once past this sweet spot, if the RPM continues to rise to 5,000, 6,000 RPM, or even higher, the engine will face devastating resistance. The enormous mechanical friction generated by the extremely fast up and down movement of the pistons, coupled with the pumping loss where the intake and exhaust valves opening and closing too briefly, leaving the engine gasping for air, will make fuel consumption skyrocket exponentially and even cause the engine to overheat and disintegrate. Therefore, the gearbox of an ICE vehicle, in essence, is not some great inventions meant to pursue ultimate efficiency. It is a massive physical patch that had to be installed to compensate for the engine's innate defects. When starting, the engine is weak, so it needs first gear to amplify the feeble torque with a large gear ratio, but also because the gear ratio is too large. If the vehicle speed increases slightly, the engine RPM will max out once on the highway to prevent the engines at high RPMs from being dragged down by massive friction and exhaust resistance. The gearbox must shift to the highest overdrive gear, forcibly pulling the engine RPM back to 2,000, which is the low fuel consumption comfort zone where resistance is lowest and combustion is most stable. In summary, shifting gears in an ICE vehicle is to rescue the engine from the high RPM resistance, held back to the efficiency zone. But if an EV is forcibly equipped with a gearbox to lower the RPM, it will instead be kicked out of its high-efficiency zone due to surging copper losses. The motor's torque characteristics are completely opposite to an engine's. The instant power is supplied. It can unleash 100% of its maximum torque at 0 RPM. In electrical engineering, this is called the constant torque region. So EVs are at their peak right from the start, requiring absolutely no gear amplification, nor a clutch to prevent stalling. When the RPM exceeds a critical point, the rated speed, usually around 4,000 to 5,000 RPM, the motor enters the so-called constant power region. At this point, although the torque limit will slowly decrease as the RPM rises, the remaining torque it can provide to handle the wind resistance of highway cruising is absolutely more than enough. Modern electric motors between 3,000 and 9,000 RPM have a very broad high-efficiency bowl. The energy conversion efficiency is almost entirely above 90%, since the motor is extremely efficient and generates no heat at 8,000 RPM. What possible reasons do we have to add a mechanical gearbox weighing hundreds of kilograms and full of gear friction losses? Not only does it take up chassis space that could have held batteries, but also every time you step on the clutch to shift gears, cutting off power, you completely ruin your EV's most powerful kinetic energy recovery system. In engineering, this is called putting the cart before the horse through and through. The reason we think cars need a clutch, need a gearbox, is because our brains have been conditioned by the flaws of the internal combustion engine over the past 100 years. We took the crutches meant to fix a defect for granted as common sense. In the EV era, the real gearbox is that silicon carbide inverter hidden in the chassis, turning on and off tens of thousands of times per second, using microsecond level switching of semiconductors. It precisely sculpts the perfect current the motor needs, replacing the bulky and friction-filled metal gears. This is a dimensional downgrade strikes from the mechanical era into the electronic era. Next time a veteran driver tells you, again, that adding a gearbox to an EV to lower RPM saves more power, please tell them this physical truth about cruising at 120 kilometers per hour, the motor hitting 8,000 RPM, and surging copper losses, to completely smash this century-old mechanical myth.